Hello, in this lecture, we're going to delve into linear algebra for artificial intelligence. Artificial intelligence itself incorporates a vast amount of mathematical concepts. Not only geometry, but also linear algebra and statistics are among the various mathematical elements heavily involved. Among these, linear algebra is considered one of the key mathematical theories in an artificial intelligence. Hence, without a solid understanding of linear algebra, you might find it challenging to read AI research papers or develop your own AI models, often requiring considerable efforts and time. Therefore, having a basic understanding of linear algebra enables an easier and more convenient approach to AI, which is why we're conducting this linear algebra lecture for AI. Linear algebra itself is a somewhat complex field of study, and it has a long history as well. So covering the entirety of linear algebra can be quite complex and difficult. So we'll review the linear algebra theories commonly used in AI and see how they're applied in AI in this lecture. I've listed 3 keywords here: vectors and matrices, their geometric meanings, and how they're used in AI. These 3 topics are not everything about linear algebra, and they don't cover the entire field of linear algebra, but they are essential elements for understanding AI. Technically, our last topic, application to AI, is about how linear algebra is used in AI, so the first 2 topics are more crucial when studying linear algebra. Linear algebra is a study of numbers, and although it's a study of numbers, it's primarily focused on the operations of vectors and matrices. You might not be familiar with the terms vector and matrix, but you can think vectors and matrices as an arrangement or a collection of numbers. A vector is a collection of numbers arranged either vertically like this or horizontally like this, representing a series of numbers in a row or a column. Matrices, on the other hand, are 2-dimensional structures formed by vectors. We'll look into the functions of vectors and matrices and how operations involving them can be applied. In linear algebra, operations are crucial, with addition and scaling being considered the most important. As a side note, we also have subtraction operation, naturally followed by addition. Scaling, or scalar multiplication, is similar to multiplication, but it also includes different elements. Scaling is similar to simple multiplication using natural numbers we learned in elementary school, and that's why we call it scalar multiplication. You might feel unfamiliar with the terms, but it's crucial to understanding that multiplication here differs from the general concepts of multiplication. So keep in mind that we have the operations of addition and subtraction, as well as scalar multiplication. It's important to note that scalar multiplication and multiplication for numbers are different, and scalar multiplication is for vectors and matrices. Now let's explore the types of data to which addition, subtraction, and scalar multiplication can be applied, as well as how these operations can be applied to those data. Here, I've listed different types of data. Essentially, most things in our world can be considered data. For example, images, languages, and numbers, all these are data. Let's see why they're data. In the case of images, they represent visual elements on a plane. But if you look at an image on screen more closely, they're composed of very small units called pixels. So when we talk about resolution, for each pixel in the image, they are given values for colors like RGB. Therefore, an image essentially has dimensions of x and y, each representing the length and width of the image. Plus, for each pixel, there are RGB values, so x representing the length, y representing the width, and RGB values together make an image 3-dimensional data. In the case of languages, my voice is recorded over time while I speak, and it forms time series data. What about words? Consider the word scalar. Scalar is composed of 6 letters S, C, A, L, A, R, arranged in a row, and each letter requires memory. Thus, words are data as well. Similarly, numbers like 3 or 6, dates April 9th, and times like 12:15 are also forms of data. Therefore, it's necessary to understand the forms this data can take. There are various forms including the ones introduced earlier, but let's discuss a few key ones. Let's talk about points first. Points are literally dots, and they are data defined by a single point. Let's think about this conceptually for a moment. They're just a dot existing. In other words, it either exists or it doesn't. In the case of scalars, we're talking about one-dimensional data. We all know about one-dimensional data because we've learned about them in elementary school. We learned about the number line where we place a 0 at the center. And then, in the early years of elementary school, we learned about moving forward to 1, 2, 3, and so on. As we progress, we learned about negative numbers, realizing that the number line also extends backward. So, scalars belong to one-dimensional data. And they're the data that can be represented by some number on this number line. Vectors, on the other hand, start increasing in dimensions. They are two-dimensional data. You can think of two-dimensional data as having two number lines. We can draw a vertical number line crossing the horizontal one. Let's call this vertical one y. It can also go 1, 2, or -1, -2. Now, how can you represent data here? In this case, data are points on the plane. Points have both x and y information at the same time. It holds two pieces of information. So, for example, if I want to represent a certain data point, and it's located over here, then its x information is -2 and y information is -1, meaning this data has a value of -2 and -1. In the case of one-dimensional scalars, this data only had the x information of -2, but when it becomes a vector, dimensions increase like this. Dimensions can grow further. Although we are talking about 2 dimensions, obviously dimensions can increase even further. Let's think about a third axis coming out of the screen. And we'll call the axis z. So there's also a value coming out of the screen. Suppose the value coming out of the screen is 3. So if it's -2 and -1, and it comes out 3 units from the screen, now we have 3 information within the point. -2, -1, and 3. Earlier, I said a vector is a two-dimensional data, but it doesn't mean that there are 2 axes, and the number of axes can grow larger. They can grow, but still all of the information can be represented as a single line of scalars. That's why it's a vector. Vectors can be thought of as lists of scalars lined up one after another. Of course, the mathematical definition might be slightly different. But for now, if every information is listed in a single line, we'll call it a two-dimensional data. So what is a matrix then? You can think of a matrix as a two-dimensional vector. What I mean by a two-dimensional vector is that in a matrix, vectors are lined up as scalars are lined up in a vector. A tensor is a two-dimensional version of a matrix, and a higher dimensional tensor is a two-dimensional version of that tensor. Theoretically, saying a vector is two-dimensional and a scalar is one-dimensional, well, that's not exactly a mathematical definition. But, to summarize, a scalar represents numbers like 1, 3, or 5, and they're the numbers themselves. A vector has one more dimension, so it's a collection of scalars. When these vectors go up one more dimension, vectors stack up and stack up and stack up, and eventually showing this form. And we call it a matrix. So you can think of dimensions of data as going up one at a time. Let's see how we represent this data. For example, these scalars are numbers, and numbers like 1, 3, or even pi are scalars. So these scalars belong to the real number domain. Or if it's something like 1 plus 3i, it's a complex number, so it belongs to the complex number domain. So we can express the scalar as an element of a set like this. Scalars can belong to real numbers, integers, or even natural numbers. If they belong to integers, we represent with the capital Z. And if they belong to natural numbers, we represent with the capital N. Thus, scalars belong to a certain number system. Let's think about vectors. Vectors can be thought of as a list of 2 scalars like this, or a list of 3 scalars, or it can even be a list of 5 scalars like this. That's why I said it's not mathematically correct to say that vectors are two-dimensional earlier, and it's more accurate to describe vectors as data with one higher dimension than a scalar. So, this one has 2 numbers, right? Since there are 2 real numbers, this vector is a collection of 2 real numbers. This one is a collection of 3, and this one is a collection of 5 real numbers. So if a vector is an element of Rn, it means that inside the vector, there are n real scalars, or real numbers. That's the correct way to describe dimensions of vectors. So the basic representation of a vector looks like this. Let's talk about matrices. As introduced earlier, the dimension of a matrix is one higher than that of a vector. I will write a new matrix on the board. It contains 3 vectors written horizontally. Inside the matrix, we have a couple of pieces of information to consider. The matrix is composed of 3 vectors, and each vector is a vector of 4 scalars. And this is how we represent this matrix. The number of rows is 3, and the number of columns is 4. So we write the number of rows first, and then write the number of columns. And that's the size of the matrix. Suppose we have a matrix A. If the matrix belongs to n by m matrices, what does it mean? It means that the vertical length of the matrix is n, and the horizontal length is m, defining the size of the matrix. Now let's shift our perspective a bit. If we have a data A from n by 1 matrices, what does it mean? It means that the vertical length of the data is n, and the horizontal length is 1. Thus, it's a vector. What if our data is from 1 by n matrices? The vertical length of the data is 1, and the horizontal length of the data is n. So it's a vector as well, just written horizontally. So even if our data look like matrices, they're still vectors. Be careful not to be confused even when they look like matrices. Lastly, let's talk about tensors. What are tensors? They're like matrices stacked up. So it gets a bit more complicated. Let's consider an image. Say it has a resolution of 360 by 480, and each pixel has RGB data of 3. So the dimension of the data is multiplied by 3. In the case of tensors, for higher dimensional data, you just multiply the dimensions like this. For higher dimensional tensors, we just multiply additional dimensions. That's how we define dimensions of tensors. So far, we've defined dimensions of scalar, vectors, and matrices, and even tensors. Let's summarize. A scalar is just a number in a certain number system. A vector is just a list of scalars with one higher dimension. The dimension of a matrix is higher than the dimension of a vector by 1. Lastly, tensors represent any data with higher dimensions, and it can go even higher. That's why the earlier explanation of dimensions like scalar is one-dimensional and vectors are two-dimensional are not accurate. They were just to show the increase in dimensions. Scalars are just a single element while vectors have length. Matrices have length and width, and tensors have length, width, and even depth. Please remember the meanings of dimensions and how we can describe them. Let's explore vectors in more detail. As mentioned earlier, vectors are collections of scalars and they belong to Rn. Again, they are collections of scalars and they have n scalars inside them. One important concept related to vectors is linear independence. But before delving into the concept of linear independence, let's discuss the functions of vectors. We'll begin with vectors in R2 since they are easier to visualize. What are vectors in R2? They are basically coordinates on a plane like 1, 3 or 2, 4. On the board, we have a plane with two axes, x and y. We can draw a point 1, 3 and another point 2, 4, which we'll call vector A and vector B respectively. Coordinates provide a simple way to represent vectors on a two-dimensional plane. Now let's delve into vectors on a two-dimensional plane. We can represent vectors with coordinates, but they have directions as well. In other words, vectors can be represented as points, but they can also be represented as arrows pointing to their coordinates. For instance, let's say we have a vector A pointing to a coordinates AB. We can say vector A is in R2 with coordinates AB. Let's draw another vector on the plane called B with values C and D. Then B is also a vector in R2 with coordinates C and D. So far, we've defined two vectors A and B. Now let me explain what linear independence is. It would be helpful to understand if you think linear independence of as how distinct each vector A and vector B are. Let's take vector A as an example. We'll start by extending the arrow or vector A in its current direction, adding straight lines both forwards and backwards. Similarly, we can extend vector B in its own directions both forward and backwards. As a result, vector A and vector B now have their own distinct spaces represented by lines extending from each vector. These lines are on a two-dimensional plane. However, these lines represent R1, which is a space of scalars. Therefore, the lines extended from vector A and vector B correspond to scalar spaces, or R1. In the two-dimensional plane, we have two lines representing R1. Now imagine there's a person walking along these lines. Suppose this person can only move parallel to vector A and vector B, either in the same or opposite as these vectors. Can you reach any point on the plane just by moving along these two lines? Put differently, can we find a path to any point on the plane by only following the direction of these two lines? This scenario provides an easy way to understand linear independence. It's about figuring out if we can reach any given point on the plane by solely moving in the directions of these two lines. Let's draw a straight line on the plane. The line can have two opposing directions, and we can define vector A along the line. Next, we'll add another straight line on the plane and define vector B on it. If we can find the path to any point on the plane by following either the same direction or the opposite direction as vector A and vector B, then we say that the vectors A and B are linearly independent. However, if we can cover the entire plane using only these two vectors, we consider them to be linearly dependent. When do two vectors become linearly dependent? Let's draw a straight line on the plane and define vector A along it, then we'll define vector B along the same line. Despite their opposite directions, when you try to combine them in various ways, like splitting each vector and merging them, there are points on the plane that remain unreachable. In such cases, the two vectors are considered linearly dependent. For instance, let's take vector A with coordinates 4, 2, and vector B with coordinates -2, -1. Regardless of how you combine them, reaching certain points on the plane becomes impossible. I'll delve into a more mathematical explanation of linear independence. Suppose we have vector A with coordinates AB and vector B with coordinates CD. If we can construct any point on the plane using the form alpha A plus beta B, then vectors A and B are considered linearly independent. Here, alpha and beta represent scalars. A simpler but less formal definition is that two vectors are considered linearly independent when we can reach any point on the plane by splitting and merging them. Let's test if we can reach this point over here using vectors A and B. First, we move along the directions of vector A by a certain distance. Then we can reach our destination by drawing a straight line starting from this point parallel to vector B. Vector addition is simply drawing a line in the direction of the first vector by a certain amount, and then drawing a connecting line in the direction of the other vector. Suppose we have vector A, vector B, and vector C, which is the result of adding vector A and vector B. How do we define vector C? Once more, we follow vector A until it reaches its end. Then, starting from the endpoint of vector A, we draw vector B. Vector C is the resulting vector connecting the origin to the endpoint of vector B. It's important to recall that if we can span the entire plane through vector addition between two vectors, then those vectors are considered linearly independent. Now let's define a basis. Consider two vectors A and B on a plane. Since they are linearly independent, they can construct the entire plane through vector addition. For instance, if we pick any arbitrary point on the plane, we can draw a straight line in the direction of vector B first, and then draw the second line in the direction of vector A. Let's consider a basis for Rn. As we need at least two vectors to construct R2, we need at least n vectors to construct Rn space. If we can find n vectors that construct n-dimensional space, we refer to those n vectors as the basis of Rn, indicating that they span Rn. This is the essence of the definitions of basis and span. Imagine we have two arbitrary linearly independent vectors. Can they form the basis of R2? Absolutely. By adjusting the length of these vectors, we can create infinitely many bases for R2. However, in the standard basis for R2, the vectors have a unique length of 1. To summarize, in the basis for Rn, there are n vectors, and together, they span the entire Rn. As mentioned earlier, matrices can be seen as collections of vectors. Similarly, the basis of Rn consists of a collection of vectors that span Rn. Let's consider two vectors, A with coordinates 2, 1, and B with coordinates 1, 2. Since vectors A and B can span R2, they form the basis for R2. But how? Through vector addition, represented as alpha A plus beta B. Using this form, the new x value becomes 2 alpha plus beta, and the new y value becomes alpha plus 2 beta. Any coordinates in R2 space can be expressed using this form. Let's arrange vector A and vector B in a matrix, writing each vector vertically. The first column represents vector A, and the second column represents vector B, forming a 2 by 2 matrix with values 2 and 1 in the first column, and 1 and 2 in the second column. Within this matrix, we have two vectors from the basis of R2. Although their length may be not 1, as it's not the standard basis for R2. Since we have two vectors in the matrix and these vectors span R2, we say that the rank of the matrix is 2. We can construct any vectors in R2 with those vectors in the matrix. Now consider a 3 by 3 matrix. This matrix comprises three vectors labeled as A, B, and C. Can we span the three-dimensional space with these vectors through vector addition? Let's introduce the third axis, Z. By scaling each vector with alpha, beta, and gamma, they can represent any point in R3. Thus, the rank of this matrix is 3. So is it always true that the rank of the matrix is always the same as the length of its width? Not necessarily. Let's draw a straight line on a two-dimensional plane. We'll place 2 points on the same line. The resulting matrix will be a 2 by 2 matrix with values 2 and 1 in the first column, and 4 and 2 in the second column. What's the rank of this matrix? The answer is 1. Let me explain why. We cannot reach a point here with a linear combination of these two vectors, as they have the same direction. Therefore, there are points on the plane that cannot be reached by these two vectors, resulting in a rank of 1 for the matrix. Let's practice with another example. Is it possible for a matrix to have rank 2 in a three-dimensional space? If a matrix has a rank of 2 in a three-dimensional space, it means that the vectors in the matrix can only span a two-dimensional plane within the three-dimensional space. For instance, if you draw an axis Z, these vectors may only span a two-dimensional plane like this. The rank of the matrix in a three-dimensional space can be 1 as well if the three vectors can only span a line. Here's an example of a matrix with a rank of 1, with values 1, 0, 0, 2, 0, 0, and 3, 0, 0. No matter how you scale the values of y and z for these vectors, they cannot be adjusted. You can only adjust the x values in this scenario, and the span of these vectors will be along the x-axis. That's why the rank of the matrix is 1. Let's illustrate with an example of a matrix with rank 2 in a three-dimensional space. Despite having 3 vectors within the matrix, leaving the last vector, if you scale the first vector by 2, you obtain the second vector. Consequently, the rank of the matrix decreases by 1. Let's summarize. When does an n by n matrix have a rank of n? An n by n matrix has a rank of n only when all of its n vectors are linearly independent. However, if the vectors are linearly dependent, the rank of the matrix will be less than n. Let's explore the mathematical conditions for linear independence. If you have vectors a and b that are linearly independent, each vector should extend along a different line. In other words, the lines extended from each vector should intersect at a point rather than overlap. Conversely, if we can construct vector a by scaling vector b, then these two vectors a and b are linearly dependent. Mathematically, a linear combination of two vectors should not always result in 0 when they are linearly independent, because this would imply they lie on the same line. There should not exist a combination of alpha and beta where the linear combination of the vectors equals 0. That's the mathematical conditions for linear independence. Let's suppose we have a matrix or a collection of vectors denoted as A. There are 3 vectors inside the matrix, and the vectors inside the matrix are 1, 2, 0, 0, 0, 1, and -1, 1, and 0. Matrix A is a 3 by 3 matrix. Now let's determine if each vector in the matrix is linearly independent and capable of spanning 3-dimensional space. We'll label each vector as A, B, C respectively. To begin, we'll examine vectors A and B for linear independence. We'll employ the form alpha A plus beta B. The resulting linear combination of vectors A and B will yield alpha, 2-alpha, and beta. Is there any combination of alpha and beta that results in 0? Yes, but only when both alpha and beta are 0. However, if vectors A and B are linearly dependent, there is another combination of alpha and beta besides 0 and 0 that would yield 0. So we've established the vectors A and B are linearly independent. Now what about vectors A and C? When we combine vectors A and C, we get alpha minus beta, 2-alpha plus beta, and 0. Is there a way to make this combination equal to 0? Well, setting alpha minus beta and 2-alpha plus beta equal to 0 gives us 3-alpha equals 0 when we add the equations together. This means that both alpha and beta must be 0. Consequently, 0 and 0 is the only combination of alpha and beta that results in a linear combination of 0, confirming the linear independence of vectors A and C. Similarly, vectors B and C also prove to be linearly independent. Hence, every pair of vectors in the matrix is linearly independent, resulting in the matrix achieving a full rank of 3. Let's consider a new matrix A consisting of 3 vectors. Let's denote the first vectors as A and B, respectively. When we combine alpha times vector A with beta times vector B, we obtain alpha minus beta, 2-alpha minus 2 beta, and 0. Can we get 0 for each value? Yes, when both alpha and beta take on the same value, whether it's 3, 4, or any other value, the resulting combination equals 0. Put simply, whenever alpha equals beta, the resultant value will be 0. Consequently, vectors A and B are linearly dependent, and the rank of the matrix decreases by 1, making it 2. When the rank of a matrix decreases, it implies the existence of a vector that when multiplied by the matrix yields a result of 0. In simpler terms, there's a vector that when multiplied by the matrix A produces a result of 0. But before delving deeper into this vector, we need to know how matrix and vector multiplication operates. So let's take a look at the basics of matrix and vector multiplication. Suppose we have a vector in Rn, which is essentially an n by 1 matrix. We'll introduce a new n by n matrix denoted by A, and then multiply matrix A by vector x. Can you guess the dimensions of the resulting matrix? The outcome of multiplying the matrix by the vector will be another n by 1 matrix, which is also a vector. When we multiply two matrices A and B, where A is an A by B matrix and B is a B by C matrix, the resulting matrix C will be an A by C matrix. So the B's between A and C will vanish. Remember, we can only multiply two matrices when the inner dimensions match, meaning B and C are equal. Since the inner dimensions of matrix A and vector x are both n, the resulting matrix is an n by 1 matrix. So when the inner dimensions are the same, multiplying a matrix by a vector yields a vector. Now let's delve deeper into how this operation functions and what implications the result holds. Let's explore matrix vector multiplication within a two-dimensional plane. Consider the equation Ax equals 0. Let matrix A be defined by the vectors 1, 2, and 2, 4. We'll denote each vector as A and B. Let's plot vector A and vector B on a two-dimensional plane. So this is vector A, and this is vector B. When we plot these vectors on the same plane, we observe that we can obtain vector B by scaling vector A by 2. Therefore, one method to obtain 0 from the two vectors is to scale vector A by 2 and then subtract vector B. Consequently, we can satisfy the equation by multiplying vector -2 and 1, making the right-hand side of the equation 0. In other words, when alpha times vector A plus beta times vector B equals 0, we can substitute -2 for alpha and 1 for beta. Let's plot the new vector -2 and 1 on the plane and denote it as x. Vector A and vector B span a straight line rather than the entire plane. Now let's consider another straight line perpendicular to this line. Since the coordinates of vector A are 1 and 2, this line will pass through the coordinates -2 and 1, which corresponds to vector x. Thus, vectors A and B can only span a straight line instead of the entire plane, while our new vector x allows them to span the entire plane. Once more, vectors A and B only cover a line, leaving some points on the plane unobtainable. However, vector x enables them to span the entire plane. The original straight line spanned by vectors A and B is referred to as the range space, while the remaining space on the plane that was not covered by the range space is called the null space. In summary, within our two-dimensional space, there is a region we can reach by linearly combining the original two vectors. We'll refer to this uncovered area as the null space. When combined, the null space and the range space account for the entire plane. Let's revisit matrix A with values 1, 2, and 2, 4. The rank of the matrix is 1. Now let's include vector x with values -2 and 1 into the matrix, which is perpendicular to vector A. As a result, matrix A becomes a 2 by 3 matrix, and its rank increases to 2. In other words, the 3 vectors within the matrix can span the entire plane. Since vectors 1, 2, and 2, 4 are linearly dependent, removing one of them from the matrix still allows vectors within the matrix to span the entire plane. Therefore, the remaining 2 vectors, 1, 2, and -2, 1, serve as the basis vectors for a 2-dimensional space, capable of spanning the entire plane. Remember, if there's a non-zero vector x that satisfies Ax equals 0, the space defined by vector x is known as the null space. Additionally, the presence of linearly dependent vectors in the matrix leads to a reduction in the matrix rank. Therefore, we can view a matrix as a linear operator. In a matrix vector multiplication of the form Ax equals b, where A is a matrix and x and b are vectors, matrix A acts as a linear operator that transforms vector x into vector b. Again, matrix A acts as a linear operator that transforms vector x into vector b. Imagine there's an unknown box that takes vector A as an input and produces vector b as output. Inside this box, matrix A is multiplied by vector A. Thus, the matrix itself functions as a linear operator. Now let's delve into the concept of a linear operator and its operation on a 2-dimensional plane. For instance, consider a matrix composed of vectors A and B, where A is 1, 2, and B is 2, 1. The rank of the matrix is 2, and it's a full rank matrix. Let's multiply this matrix by a vector x1 and y1. Because we're scaling vector A by x1 and vector b by y1, the outcome of the matrix vector multiplication is x1 plus 2y1, 2x1 plus y1. If the vector x1, y1 is 1 and 1, the outcome of the equation yields the vector 3 and 3. In simpler terms, when the initial vector 1 and 1 is the input of the matrix vector multiplication, it yields a new vector 3 and 3 as output. What does it signify that the original vector 1 and 1 has shifted to its new coordinates 3 and 3? Let's examine this more closely. On our 2-dimensional plane, this vector is positioned at coordinates 3 and 3. In other words, the point's coordinates are 3 and 3 on a 2-dimensional plane, where the axes are labeled as the x-axis and y-axis. Now let's imagine that instead of the x-axis and y-axis, the same plane is depicted using vector A and vector B as its new axes. Once more, we are visualizing the plane from a perspective that utilizes vector A and vector B as the new axes. To reach the points at coordinates 3 and 3 on the plane, we start by moving along vector A, and from the endpoint of vector A, we continue by moving along vector B. Therefore, the coordinates of the points are 3 and 3 on the plane when using the original x-axis and y-axis. However, when using vector A and vector B as x's, the new coordinates of points become 1 and 1. Let me elaborate on the significance of shifting coordinates from 3 and 3 to 1 and 1. Consider if the two-dimensional space initially used vectors a and b as its x's. In this scenario, the coordinates of point would be 1 and 1. The change in coordinates imply that when using the x-axis and y-axis, the coordinates are interpreted as 3 and 3. Therefore, multiplying a matrix by a vector signifies adjusting or rotating the original axis towards the vectors in the matrix. Let's consider a matrix A with values 1, 2, 2, and 1. We'll draw lines passing through the coordinates in the matrix and the origin, which will serve as the new axis of the plane. Denoting each vector in the matrix as A and B, we'll refer to the corresponding lines as A and B respectively. On line A, we can designate 1, and similarly, on line B, we can mark 1 as well. These ones correspond to the vectors in the matrix. We can also label 2 and negative 1 on both lines A and B. With this setup, the coordinate space has been transformed, allowing us to determine the new coordinates of points in the plane. Matrix A has twisted the coordinate space, and we are able to identify new units or ones within this modified coordinate system. Within this new coordinate space, we can locate a point at coordinates 1 and 1, which is positioned here. Conversely, the coordinates of the same point become 3 and 3 when viewed on the plane using the original axes, namely the x-axis and y-axis. This illustrates one aspect of comprehending matrix vector multiplication. Thus, in matrix vector multiplication, a vector multiplied by a matrix represents the altered coordinates of a point within a transformed coordinate system, whereas the resulting output vector signifies the coordinates of the same point within the original coordinate space. Let's recap. When we apply matrix vector multiplication to a vector on a two-dimensional plane, the vector undergoes a shift, resulting in new coordinates as the coordinate space adjusts or twists. With this interpretation of matrix vector multiplication, we can now understand matrices from various perspectives. For example, let's take a rotation matrix. Suppose we have vector A positioned at coordinates 2, 0. If we rotate vector A 90 degrees counterclockwise, we obtain a new vector at coordinates 0, 2, which we'll denote as vector B. Let's consider this rotation of a vector as a form of matrix vector multiplication. We performed matrix vector multiplication on an unknown matrix with the vector 2, 0, resulting in a shift of the vector's coordinates to 0, 2. Any guesses on what this matrix might be? As mentioned earlier, 2, 0 represents the coordinates of a vector in an adjusted coordinate space, while 0, 2 represents the original coordinates of the same vector in the initial coordinate space. How could we adjust the axis of the plane so that the coordinates 0, 2 correspond to 2, 0? One approach could be to designate the vertical axis as the x-axis and the horizontal axis as the y-axis. Consequently, the x value of the vector would be 2, and the y value would be 0. Thus, in this new coordinate system, the vector's coordinates would be 2, 0, whereas in the original coordinate system, they would be 0, 2. So, the vectors in the unknown matrix serve as new x's that are rotated 90 degrees counterclockwise. How can we express this 90-degree rotation in a matrix? Let's consider the values 0, 1, -1, and 0 as potential entries for the matrix. Let's denote these vectors as A and B. The coordinates of vector A are 0, 1, while the coordinates of vector B are -1 and 0. That's what vectors A and B look like. Given that vectors within a matrix are treated as the new axes of a two-dimensional plane, the matrix comprised of these two vectors, A and B, rotates the coordinate space or plane by 90 degrees counterclockwise. This matrix is commonly referred to as a rotation matrix. A rotation matrix is a good example that directly demonstrates how the coordinate space undergoes a transformation. From now on, we're going to explore the multiplication between two matrices instead of a matrix and a vector. Let's see what happens when we multiply two matrices. Let's consider multiplying two matrices A and B along with a vector x. Once again, A and B are matrices and x is a vector. We'll begin by multiplying matrix B by vector x, resulting in a new vector. Then, we'll multiply matrix A by the product of matrix B and vector x, ultimately yielding another vector. To summarize, we initially had vector x, which we then multiplied by matrix B. Next, we multiplied matrix A by the product of matrix B and vector x. Let's approach this process conceptually. When we multiply matrix B by vector x, we tilt the initial coordinate space. Subsequently, by multiplying the resulting product by matrix A, we tilt the already tilted coordinate space once more. Now, let's explore matrix multiplication with BA instead of AB. First, we multiply matrix A by vector x. Then, we multiply matrix B by the resulting product of matrix A and vector x. So, does the order of matrices in matrix multiplication matter? Yes, because AB initially transformed the coordinate space with matrix B first, whereas BA transforms the coordinate space with matrix A first. Hence, the order of matrices in matrix multiplication is significant. For instance, rotating the coordinate space before flipping it could yield different coordinates compared to flipping it first and then rotating it. Once more, unlike general multiplication involving natural numbers, the order of matrices in matrix multiplication can yield different results. Therefore, I want to emphasize that AB is not equal to BA and AB minus BA does not always equal 0. As explained, the reason why the product of matrices varies depending on the order of matrices can be understood by examining the order of transformations applied to the coordinate space. If you have prior experience with linear algebra, you might recognize some of these terms on the board. Let A be a 2x2 matrix with values A, B, C, and D. The transpose of matrix A is obtained by interchanging its rows and columns. Initially, we wrote vectors in the matrix vertically. However, in a transpose matrix, vectors are written horizontally, with each row of the matrix becoming a vector. If matrix A is equal to its transpose, we refer to the matrix as a symmetric matrix. It's important to note that the symmetric matrices always have an equal number of rows and columns. On the other hand, if the transpose of matrix A is equal to its negative, we refer to the matrix as a skew-symmetric matrix. A diagonal matrix is a square matrix where all elements outside the main diagonal are 0. The main diagonal of a matrix consists of the elements where the row index equals the column index. A triangular matrix is a special type of square matrix where all the entries above or below the main diagonal are 0. Depending on whether the non-zero entries are above or below the main diagonal, we classify triangular matrices into two types: upper triangular matrices and lower triangular matrices. So far, we've learned that the multiplication between a matrix and a vector results in a transformation of a coordinate space, and we'll apply this concept to understand the fundamental principles of neural networks. Let's delve into the basic structure of neural networks. Initially, we have data, which serves as an input, and this data passed through a hidden layer before ultimately being returned as output. Let's denote the data as x, the weights and bias in the hidden layer as w and b, and finally the output as y hat. Then, the output y hat is determined by the activation function sigma applied to wx plus b. Let's explore how multiplication between a matrix and a vector operates within this process. Let's say the data x is a vector in Rn. The weights and bias in the hidden layer also have their own dimensions. Consider that the weights take the form of a matrix. Suppose the output y hat is a vector in Rm. Since the dimensions of y hat and x are m and n respectively, the weights w must be a m by n matrix, and the bias must be a vector in Rm. To clarify, w is an m by n matrix, and b is a vector in Rm. The first letter here is m. Suppose the data x is an image, and the output y hat is a list of labels of the image. In this case, n is much larger than m. Let's revisit the equation from the previous slide. Y hat equals sigma wx plus b. The length of vector x is very long since its dimension is n by 1. On the other hand, the vector y hat is shorter compared to x, with its dimension being m by 1. Meanwhile, w is an m by n matrix, and b is also a vector in Rm, specifically m by 1 vector. In the equation, we begin with vector x in Rn. Initially, we multiply an m by n matrix w by vector x. Do you remember what it means to multiply a matrix by a vector? The matrix vector multiplication transforms the original coordinate space. Up to now, we are only familiar with transformations of a coordinate space by square matrices, such as a 2 by 2 matrix. However, in our equation, the number of rows and columns of weights w are different. The dimension of the input is n by 1, while the dimension of the output is m by 1, indicating that the information in the input has been compressed to lower dimensional data. In other words, the input x exists in a high dimensional space, while the output exists in a lower dimensional space. Thus, the weights matrix W not only distorts the original coordinate space, but also reduces its dimensionality. Stated differently, you can also decrease the dimensionality of a space through a matrix vector multiplication when the number of columns of the matrix is larger than the number of rows. Now, let's discuss why we need an activation function in neural networks. Transforming a coordinate space, such as rotating and resizing, are all linear transformations. However, sometimes we need to introduce curvature or remove linearity from the axes in the space to extract meaningful information from the data. That's why we apply an activation function to the product of weights and data. Some of the most popular activation functions include sigmoid, ReLU, or hyperbolic tangent functions. These functions introduce nonlinearity to the space. So the fundamental concept of neural networks is to extract essential dimensions from the data by distorting and reducing the dimensions of a coordinate space. The objective of training neural networks is to find weights W and bias B that enable us to transform a coordinate space and reduce dimensions until we obtain crucial information from the data. Now, let's delve into the addition formulas for sine and cosine by using the transformation of a coordinate space. Some of you may already be familiar with these addition formulas, which facilitate the calculation of sine and cosine for sums or differences of angles. Let's explore how these formulas can be explained within a coordinate space. To begin, let's define two matrices. The first matrix rotates the coordinate space by alpha degrees. And the second matrix rotates the space by beta degrees. Now, let's see what these rotation matrices look like. A rotation matrix are comprising cosine theta, negative sine theta, and cosine theta, rotates the coordinate space by theta degrees. Let me explain how this matrix rotates the space. When we multiply the matrix by a vector, it gives us a new vector. Suppose the input vector is 1, 0. After the multiplication, the output vector will have values cosine theta and sine theta. If we plot this new vector on a two-dimensional plane, the angle between the two vectors is theta. Another way to think about this is that the coordinates of the same vector in the transform space becomes 1, 0, while in the original space, coordinates are cosine theta and sine theta because the coordinate space has been rotated. So in this transformed coordinate space, the vector's coordinates are 1, 0. Let's revisit the addition formulas for sine and cosine. Earlier, we had two rotation matrices. We'll call the first matrix, which rotates the space by alpha degrees, A, and the second matrix, which rotates the space by beta degrees, B. Now imagine we have another rotation matrix, C, which rotates the space by the angle alpha plus beta. Matrix C is the result of multiplying matrices A and B. Unlike most cases where the order of matrices in multiplication matters, with rotation matrices, it doesn't. So the result of matrix multiplication AB and BA are the same. Let's manually multiply the two matrices, starting with matrix B. The entries on matrix B are cosine beta, negative sine beta, and cosine beta. The entries of matrix A are cosine alpha, negative sine alpha, and cosine alpha. The first entry in the product of the two matrices is cosine beta times cosine alpha minus sine alpha times sine beta. The next entry is sine alpha times cosine beta plus cosine alpha times sine beta. Using the addition formulas for sine and cosine, these expressions simplify to cosine alpha plus beta, sine alpha plus beta, negative sine alpha plus beta, and lastly, cosine alpha plus beta. The first column of the resulting matrix aligns with these addition formulas. This example demonstrates how the multiplication of two rotation matrices can be understood through the lens of the sine and cosine addition formulas. Determinant is also a term frequently used in linear algebra. Let's explore the determinant of matrix A. Suppose we have a matrix A with values A, B, C, and D. We can calculate the determinant of matrix A by finding the value of A times D minus B times C. However, we're going to discuss the geometric interpretation of the determinant. Let's plot the two vectors represented by matrix A on a two-dimensional plane. Suppose A and C are 2, 1, and B and D are 1, 2. These two vectors on the plane represents each vector. We'll use the vectors 2, 1 and 1, 2 as the new axes of the plane. Under this new coordinate system defined by the two vectors, we can plot a point at coordinates 1, 1, which was originally located at 3, 3 in the original coordinate space. Now let's calculate the area inside the parallelogram formed by these vectors. One straightforward method to calculate the area is by dividing the parallelogram into smaller pieces like this. Considering that the area of the square containing the parallelogram is 9 and the area of the space not covered by the parallelogram is 6, we find that the area of the parallelogram is 3. As the coordinates in the transformed coordinate space are 1, 1 and in the original coordinate space are 3, 3, this illustrates what the matrix vector multiplication looks like. Using the formula above, we can calculate the determinants of matrix A, which is 4 minus 1 equals 3. Let's interpret the value of the determinant of the matrix conceptually. In the transformed coordinate space, each vector in the matrix defines ones. In the transformed coordinate space, the length of both vectors and the area of the parallelogram are 1. However, in the original coordinate space, the area of the parallelogram is 3 as we measured. So the determinant of matrix A signifies that the area of the parallelogram increases by 3 in the original coordinate space from 1 to 3. Now, let's imagine we increase the length of one side of the parallelogram to 2. The coordinates of the vector change to 2, 1 in the transformed space and 5, 4 in the original space. Let's observe how this change affects the area of the parallelogram. We'll scale the vector 2, 1 by 2, resulting in coordinates of 4, 2. Connecting vector 1, 2 to this scaled vector forms a new parallelogram. To measure its area, we split the square containing the parallelogram. The total area of the square is 20, with the uncovered area of 14, leaving the parallelogram's area as 6. In the transformed space, the parallelogram's area is 2, while in the original space, it increases to 6. Once again, we observe that the area of the parallelogram increases by 3, which corresponds to the determinants of the matrix. This method provides a straightforward explanation of the determinants of a matrix. Sometimes, the value of a matrix determinant is less than 0. Consider matrix A with entries 1, 2, 2, and 1. Calculating the determinant using the formula gives us -3. This matrix contains the same vectors as the one in the previous slide, but their order has changed. This change in order is why there's a negative sign in front of the 3. Let's delve into what the negative sign in front of the 3 signifies. In a typical two-dimensional plane, we usually label the horizontal axis as x and the vertical axis as y. Imagine we swap these labels. This switch results in a negative determinant. Here's why. To switch the labels of the axes, we need a new matrix. When a vector's coordinates on the plane with switched axes are 1, 0, its coordinates in the original space become 0, 1. Let's check the transformation of the coordinates in matrix vector multiplication. To achieve this transformation through matrix vector multiplication, we use the matrix 0, 1, 1, 0. This matrix has a determinant of -1. Therefore, switching the order or labels of the axes results in a negative determinant. In summary, a negative determinant indicates that the order of the axis has been reversed from that of the original space. Let's practice calculating the determinant of a matrix with an example. As previously explained, the determinant of a 2x2 matrix can be calculated using the formula AD minus BC. For a 3x3 matrix, we often use a method known as Cramer's rule, which you might have seen in linear algebra textbooks. Cramer's rule is sometimes referenced in AI research paper as well. So you might be interested in learning how to calculate the determinant of a 3x3 matrix. To calculate the determinant of a 3x3 matrix, we split it as follows. First, multiply the element A at the first row and first column by the determinant of the 2x2 matrix that remains after removing the row and column containing A. Next, multiply the element B at the first row and second column by the determinant of the 2x2 matrix that remains after removing the row and column containing B. Lastly, multiply the element C at the first row and third column by the determinant of the 2x2 matrix that remains after removing the row and column containing C. Therefore, the determinant of this 3x3 matrix is computed as A times the determinant of the 2x2 matrix formed by the second and third rows of the second and third columns, plus C times the determinant of the 2x2 matrix formed by the second and third rows of the first and second columns, minus B times the determinant of the 2x2 matrix formed by the second and third rows of the first and third columns. The reason for the negative sign in front of B, while the signs in front of A and C are positive, relates to the rules of the determinant calculation method, which alternate sign across the matrix. Specifically, the 2x2 matrix associated with B in the expansion is formed by the elements Fi and Dg. The determinant for the matrix Fi Dg is calculated as B times Fg minus Di. We put a negative sign in front of B because the order of Di and Gf is switched. To calculate the determinant of a 3x3 matrix, we split the matrix into 3 parts and sum the results from each. The process is similar when calculating the determinants of a 4x4 matrix. We divide the matrix into 4 components. The first component consists of A and the remaining 3x3 matrix. We then multiply A by the determinants of the 3x3 matrix. The second component contains B and the remaining 3x3 matrix. The remaining 3x3 matrix can be constructed like this. Then we multiply B by the determinants of the 3x3 matrix. This process is repeated for each column, and the results are summed up. In most cases, you don't need to perform this calculation by hand, so it's more important to understand the process rather than memorize it for practical applications. The determinants of a matrix can be positive, negative, or even zero. Let's explore what a zero determinant means. Consider a matrix A with elements A, B, C, and D, where the determinant calculated as AD minus BC equals 0. Understanding the meaning of a determinant of 0 is not intuitive. Previously, we discussed a matrix A with values 1, 2, 2, and 1. We can set the determinant of matrix A to 0 by changing a value within A. Let's change the bottom right value from 1 to 4. Now the determinant of this matrix becomes 0. Next, let's plot the vectors from matrix A on a two-dimensional plane. Notice that both vectors 1, 2, and 2, 4 lie in the same line. This means the vectors can span the entire space, indicating they're linearly dependent. Consequently, the rank of the matrix is 1, not 2. This scenario also implies the existence of a vector x such that ax equals 0. All of these observations are interrelated and stem from the fact that the determinant is 0. Now let's interpret the geometric meaning of a determinant of 0. Suppose we multiply matrix A by a vector x and the product is vector y. In this transformation, any vector we multiply ends up on the same line as y. Even vectors initially located outside this line ultimately align with it. Now consider an arbitrary shape or region denoted as S in the plane. Initially, on the original coordinate space, we can measure the area covered by S. However, every point within S eventually maps onto the line, resulting in an area of 0. Once more, the determinant of a matrix represents changes in area. When the determinant is 0, it signifies that every point on the plane transforms onto points along the line. Because every point on the plane transforms onto points along the line, and there are points unreachable by the vectors in the matrix, the determinant of the matrix becomes 0. When the determinant of a matrix is 0, it signifies the presence of linear dependent vectors within the matrix. This reduction in determinants also implies a decrease in the rank of the matrix, alongside the existence of a null space. Essentially, these concepts hold the same idea. Now let's explore the concept of the inverse matrix. The inverse of matrix A is denoted by A with a -1 in superscript. Previously, we learned that the order of matrices in matrix multiplication matters, and the final product can change depending on the order. Suppose we multiplied matrices A and B, and the product is an identity matrix. An identity matrix is a square matrix in which all the elements of the main diagonal are 1s, while all the other elements are 0s. It's usually denoted by the symbol I. Each vector in an identity matrix represents the axis of the original coordinate space. In other words, when multiplying the identity matrix by a vector, the matrix does not alter any coordinates or the space. Let's explore what it means when the product of two matrices A and B results in an identity matrix. As I explained earlier, the products ABX and BAX can differ because in the multiplication ABX, we first alter the coordinates with matrix B, then with matrix A. By multiplying B first and A next, we end up at the same coordinates or coordinate space. In other words, we transform the coordinates twice and the final result remains unchanged. If we multiply matrix A by a certain matrix and obtain an identity matrix as a product, we call the matrix multiplied by matrix A the inverse matrix of A. This means that an inverse matrix of A restores the coordinate space altered by matrix A. We began with a two-dimensional space defined by the axes x and y. Suppose A is a rotation matrix that rotates the space by 90 degrees counterclockwise. Let's visualize the space after it's transformed by matrix A. The inverse matrix of A restores the space back to its original state, where x represents the horizontal axis and y represents the vertical axis. Restoring the original space requires a 90-degree clockwise rotation. Therefore, the inverse matrix of matrix A is a rotation matrix that rotates the space 90 degrees clockwise. For every rotation matrix, there exists an inverse matrix that rotates in the opposite direction by the same angle. Similarly, matrices that shrink the space also have an inverse matrix, as the space can be restored to its original state by scaling the size of its coordinates. However, there are matrices that do not have an inverse. Let's consider the matrix from the previous slide that maps every point on the plane onto a single line. The vectors within the matrix are linearly dependent. After the transformation by the matrix, vectors on the plane will lose their information and be compressed to a single line as two-dimensional data is reduced to one dimension. In other words, this means that different vectors on the plane can be mapped to the same points on the line. For instance, two distinct coordinates A, B, and C, D can be mapped to the same coordinates E and F. This transformation can be expressed as a matrix vector multiplication AX. Matrix A shifts every point on the plane to a line. However, to restore the transformed space back to the original space, we lose track of where the original coordinates EF came from. This loss of information is referred to as information loss. Because of this information loss, we cannot restore the space back to its original space. Consequently, in this case, the inverse of matrix A does not exist. Now, let's explore the condition for the existence of an inverse matrix. This condition is that the determinant of the matrix must not be zero. This implies that every vector in the matrix is linearly independent, making the matrix a full-rank matrix. Earlier, we learned about the relationships between linear independence, the rank of a matrix, and the existence of the null space. Now, we understand the connections between the existence of an inverse matrix and these conditions as well. Let's return to vector operations. Previously, we learned about operations such as addition and scaling. In addition to this, the dot product, or inner product, is another important operation. The inner product is an operation between two vectors that returns a scalar. Suppose we have two vectors A and B. Let's plot them on the plane. We can calculate the similarity of the two vectors using the dot product. Understanding the dot product might not be intuitive, so I will explain it in more detail. Think of it this way. The dot product between two vectors indicates how much they can cooperate or how much they cannot cooperate. Let's replot vectors A and B so that they are perpendicular to each other, with vector A on the x-axis and vector B on the y-axis. This shows that vector A and B have different directions. Imagine two people, one on each of the vectors A and B, moving along their respective vectors. The person on vector A can only see the person on vector B when they cross at the origin where the vectors intersect. Now let's introduce the new vector C onto the plane. Unlike with vector B, the person on vector A can partially see the movement of the person on vector C by observing the shadow of vector C onto vector A. Similarly, the person on vector B can observe the movement along vector C by watching its shadow onto vector B. However, the person on vector B cannot see the movement of the person on vector A at all. When they cannot observe each other's movements through a shadow, the dot product of the two vectors is zero. When they can perfectly observe each other's movement, it's the product of the length of the vectors. Let's define the dot product mathematically. Consider two vectors A and B, with an angle theta between them. The dot product of vectors A and B is obtained by multiplying the length of both vectors and the cosine of theta. This formula allows us to calculate the dot product of two vectors. When the angle theta between the vectors is 90 degrees, they are perpendicular and cosine theta equals 0. Consequently, the dot product also becomes 0. Conversely, when the angle theta between the vectors is 0, cosine theta equals 1, resulting in the dot product being the product of the length of the vectors. Hence, the dot product can be defined using the length of vectors and the angle between them. However, there's another way to define the dot product. Let's consider vectors A and B on a two-dimensional plane. Both vectors A and B have two components. Let A be 2, 1 and B be 1, 2. The dot product of vector A and B equals the sum of the products of their corresponding components, resulting in a value of 4. Now let's delve into significance. As previously mentioned, the dot product of vectors A and B represents the relative movement of B observed from the viewpoint of A. A can perceive the movements along B by drawing a perpendicular line or shadow connecting A to the endpoints of B. Subsequently, A can partially observe the movements along B based on the angle theta. That's why we calculate the dot product by multiplying the length of the vectors and cosine theta. The length of the adjacent side of the right-angle triangle represents the product of the length of vector B and cosine theta. This product represents how much a person on vector A can observe vector B. If the coordinates of vector A are x1, y1, and the coordinates of vector B are x2, y2, then we can define a vector with a direction of this perpendicular line as negative y1 and x1. However, when conducting a dot product, we disregard this perpendicular line and only consider a line parallel to vector A. As mentioned earlier, the dot product of two vectors is calculated by summing the products of their corresponding components. When summing the products of their corresponding elements, the perpendicular components are eliminated, leaving only the parallel components. You can find the length of vector A by taking the square root of the sum of the squares of its elements x1 and y1. Similarly, you can find the length of vector B. If you calculate the product of the length of vector A and B and cosine theta, you will eventually arrive at the same values obtained by summing the products of their corresponding elements. It's crucial to remember the geometric interpretation of the dot product of vectors. We calculate the dot product of two vectors when we want to measure the relative movements between them. Thus, we can use the dot product itself as an index representing the similarity between the vectors. If the angle between the vectors is narrow, we'll get a high value for the dot product. If the two vectors are perpendicular or have a wide angle, then we'll get a low value for the dot product. From the data perspective, when the vectors are far away from each other, it means that they contain different types of information. Since they have different types of information, the similarity index has a low value. That's how we can use the dot product as a similarity index. When two vectors are perpendicular, the dot product of the vectors is 0, implying that they hold different types of information. Because vectors hold various types of information and the dot product can measure similarities or differences between them, It is often employed in the attention mechanism. The attention mechanism is a concept in artificial intelligence frequently utilized in natural language processing. Let's consider a sentence. How about using the title of this slide as an example? We have 4 words in the title, each pair of which has a similarity measure. Together, these words form a sentence. When constructing a sentence, the similarity measures between its words are typically high. Let's add a random word apple next to the title and enumerate each word. The word apple is quite relevant to the other 4 words in the title. Thus, its similarity measure is lower than that of the others. However, the similarity measures between the other words are high. Specifically, the similarity measure between dots and product is higher than the similarity measures between the other words. Let's create a table with 5 rows and 5 columns, where each row and column corresponds to a word in the title. The similarity measure between a word and itself is very high, so I will fill the diagonal boxes with the darkest color. The similarity measure between the words dots and product is also high, but not as much as the self-similarity measure. Suppose the similarity measure between dots and attention is also high. Similarly, the similarity measure between advanced and attention is high. We refer to this table as a similarity map or similarity matrix. The self-attention mechanism or attention mechanism in natural language processing defines this similarity matrix before training. Each entry in the similarity matrix holds a similarity measure, which can be calculated using the dot product. In natural language processing, words are treated as data. Thus, each word in the title is not merely a group of letters, but instead it's represented as a vector in an n-dimensional space. If the similarity measure between 2 words is high, the dot product of the corresponding vectors also has a high value. If the similarity measure between 2 words is low, the dot product has a low value. In the attention mechanism, encoding is achieved through this process. Thus, the dot product is a crucial concept. Let's summarize the concept in linear algebra we've learned so far. Suppose we have an n by n matrix A. Then matrix A is composed of n vectors in Rn. If these n vectors within the matrix are linearly independent to each other, then the following properties naturally follow. The rank of the matrix is n. The null space does not exist. The determinant of the matrix is not 0. And lastly, the inverse of the matrix exists. Let's consider another matrix A composed of n vectors. If at least one pair of vectors within the matrix is linearly dependent, then the following properties hold. There exists a null space that cannot be spanned by the vectors, meaning there exists a vector x such that ax equals 0. Moreover, the rank of the matrix is equal to the number of the vectors within the matrix that are linearly independent, and it is less than n. Consequently, the determinant of the matrix is 0. And lastly, the inverse of the matrix does not exist. Let's define the cross product of vectors as well. Suppose we have 2 vectors A and B on a 2-dimensional plane. The cross product of the vectors conveys a directional information between them. Now, consider a 3-dimensional space with vectors x, y, and z on each axis. In this three-dimensional space, there exists a vector perpendicular to both vectors x and y. Vectors x and y are already perpendicular to each other, and vector z is perpendicular to both vectors. Calculating the cross products of the two vectors x and y is related to finding vectors like z that are perpendicular to both x and y. Suppose the coordinates of vector x is 1, 0, 0, the coordinates of vector y are 0, 1, 0, and finally, the coordinates of vector z is 0, 0, 1. By calculating the cross product of vector x and y, we can determine if we can find perpendicular vector z. You can compute the cross product of vectors a and b by computing the determinant of a matrix. Arrange vectors a and b horizontally on the second and third rows of the matrix. For the I component, calculate the determinant of the corresponding 2x2 matrix as y1 z2 minus z1 y2. Similarly, for the j component, compute z1 x2 minus x1 z2. And for the k component, evaluate x1 y2 minus x2 y1 from the corresponding 2x2 matrices. Now, let's delve into the conceptual understanding of this product. Consider two vectors a and b in a three-dimensional space. As previously mentioned, the cross product of a and b is a vector perpendicular to both. Since vectors a and b lie on the same plane, the vector perpendicular to both a and b must extend out of the screen. We've discussed various topics related to vectors and matrices, such as matrix multiplication and the rank of a matrix. Moving forward, we'll delve into the concepts of eigenvalues and eigenvectors. Some of you may already be familiar with the formulas for calculating eigenvalues and eigenvectors, and you can easily find the calculation methods in a linear algebra textbook and other resources. However, in this lecture, we'll primarily concentrate on their geometric interpretations. Mathematically, an eigenvalue, often denoted by the Greek letter lambda, satisfies the equation ax equals lambda x, where a is the matrix and x is the eigenvector. In other words, it means that when you multiply matrix A by its eigenvector x, you get the same vector x back, just scaled by the eigenvalue lambda. Let's expand the equation. Suppose A is a 2x2 matrix. The left-hand side of the equation ax is simply the result of multiplying matrix A by vector x. Scaling vector x by lambda is the same as multiplying a diagonal matrix with diagonal entries of lambda by x. Eigenvalues and eigenvectors are values and vectors that satisfy the equation. These are the basic definitions of eigenvalues and eigenvectors commonly used in linear algebra. Let's quickly review the methods for calculating eigenvalues and eigenvectors. We'll rewrite the equation from the previous slide. After subtracting the right-hand side of the equation from both sides, we obtain a matrix 3 minus lambda, 1, 0, and 2 minus lambda multiplied by x equals 0. Now we need to find the values and vectors for lambda and x. This equation can be rewritten as a minus lambda I, x equals 0. We're already familiar with this form. X is a vector that constructs a null space. Additionally, x exists only when the determinant of the matrix is 0. The determinant of the matrix can be expressed as 3 minus lambda multiplied by 2 minus lambda equals 0. Thus, lambda is either 3 or 2. When the value of lambda is 3, A minus lambda I becomes a matrix with values 0, 1, 0, 0. The eigenvector is a vector that returns 0 when multiplied by the matrix. Thus, X is a vector 1, 0, and it's an eigenvector for eigenvalue 3. Let's delve into the geometric interpretations of eigenvalues and eigenvectors. Imagine a two-dimensional plane displayed on the screen. Earlier, we found that the eigenvector of matrix A is 1, 0, when the eigenvalue is 3. Now let's quickly determine the eigenvector of matrix A for the eigenvalue 2. The values in the matrix A minus lambda I are 1, 0, 0, and 0. Thus, the eigenvector is 0, 1. The eigenvector of A is 0, 1 when the eigenvalue is 2. What's the geometric interpretation of these values? Let's plot two vectors 3, 0, and 1, 2 on the plane. Denoting each vector as A and B, we proceed to transform the current coordinate space with matrix A. Consequently, coordinates of arbitrary points on the plane shift to new coordinates. For example, coordinates 1, 1 will be shifted to 4, 2. We can determine the new coordinates through matrix vector multiplication. Now let's examine why coordinates 1, 1 are shifted to 4, 2. From the endpoint of vector A, we can draw vector B, which eventually points to the coordinates 4, 2. In other words, the point at coordinates 1, 1 in the transform space is located at coordinates 4, 2 in the original coordinate system. What about coordinates 1, 0? They will be shifted to new coordinates 3, 0. Using the matrix, we can transform a coordinate space and compare changes in coordinates on the plane. There's something important to pay attention to here. Some vectors on the plane will remain on the same line even after their coordinates have been shifted by a matrix. Let's see which vectors behave like this. For example, the vector 1, 0 has been shifted to 3, 0, and both vectors lie on the same line with the same direction. Vector 0, 1 also behaves in a similar manner. If we multiply matrix A by the vector 0, 1, then we get a vector 1, 2. Oh, these two vectors don't lie on the same line. It is highly likely that I made a mistake, and 0, 1 is not an eigenvector of the matrix A. The values in the matrix A minus lambda I are 1, 1, 0, 0. If we multiply the matrix by the eigenvector for eigenvalue of 2, we get 0. Thus, the eigenvector for the eigenvalue 2 is 1, negative 1. The coordinates 1, negative 1 are in the transform space, and we can determine their original coordinates through matrix vector multiplication. The original coordinates of 1, negative 1 are 2, negative 1. By plotting these coordinates on the plane, we can see that they lie on the same line and maintain the same direction. So do you see why the vector 0, 1 is not an eigenvector of matrix A? When the coordinates of an eigenvector are transformed by a matrix, they remain on the line spanned by the eigenvector. Let's consider another set of coordinates on this line. The coordinates negative 1 and 1 will be transformed to negative 2 and 2 by matrix A. In summary, any coordinates on the line spanned by an eigenvector will be transformed to coordinates still on the same line. Furthermore, eigenvalues determine the extent of this transformation along the line. Since 2 is an eigenvalue for the eigenvector 1, -1, both the coordinates 1, -1 and -1 and 1 have been transformed by a factor of 2 along this line. Another set of coordinates -2 and 2 on the line is shifted to -4 and 4 by a factor of 2 along the line. Conversely, coordinates 1, 0 have been transformed by a factor of 3 as the corresponding eigenvalue is 3. These explanations provide a geometric insight into eigenvalues and eigenvectors. Let's explore why these lines spanned by each corresponding eigenvector are crucial. During a matrix transformation, the coordinates of a point are relocated to new positions somewhere in the transform space, while other points outside this line struggle to move their new positions. The points on this line smoothly shift along the line to their new coordinates. In other words, while the shapes of arbitrary lines can be altered by the transformation, the lines spanned by the eigenvectors remained unchanged. This highlights the significance of eigenvectors and eigenvalues in linear transformations. Let's summarize the geometric significance of eigenvalues and eigenvectors. Consider a matrix A with eigenvalues and eigenvectors. When you multiply matrix A by one of its eigenvectors, the direction of the resulting vector remains unchanged, although its length may vary. The length of the resulting vector is determined by the eigenvalue corresponding to the eigenvector. It's important to remember their geometric interpretations. However, eigenvalues aren't always real numbers, such as the case with 2 and 3 from the previous example. For instance, take a rotation matrix. If we consider a rotation matrix R that rotates space counterclockwise by an angle theta degrees, it has entries cosine theta, negative sine theta, sine theta, and cosine theta. This matrix R rotates the space by theta degrees. Let's find the eigenvalues of this rotation matrix. If matrix R rotates the space by 90 degrees, its entries become 0, -1, 1, and 0. Subtracting lambda I from the matrix gives R minus lambda I with values negative lambda, -1, 1, and negative lambda. The determinant of this matrix is lambda squared plus 1. To make the determinant 0, lambda must be either positive I or negative I. Thus, lambda is an imaginary number. When the value of an eigenvalue is an imaginary number, it implies that the corresponding eigenvector also contains imaginary numbers. This means that there are no vectors that maintain their directions after the transformation by the matrix. Let's see why. The rotation matrix R rotates the space by 90 degrees, which means the direction of every vector or line crossing the origin will be changed. Thus, imaginary eigenvalues imply that there are no vectors on the plane that maintain their direction after the transformation. So remember that if you obtain an imaginary number for an eigenvalue of a matrix, there are no vectors that maintain their directions after the transformation. Let's quickly go over some of the useful formulas related to eigenvalues. The trace of a square matrix is the sum of its diagonal elements and also equals the sum of its eigenvalues, while the determinant of the matrix is the product of its eigenvalues. Matrix diagonalization is a key concept that underscores the importance of understanding eigenvalues and eigenvectors. Let's delve into the diagonalization process. For each eigenvalue of a matrix, there exists a corresponding eigenvector. If A is an n by n matrix, there can be up to n pairs of eigenvalues and eigenvectors. If Vn is an eigenvector of matrix A, then there exists an eigenvalue lambda n such that AVn equals lambda n times Vn. Since V1 through Vn are vectors in Rn, we can represent this n equation as a single matrix multiplication. The first matrix in the multiplication is simply matrix A, while the second matrix comprises the n eigenvectors written vertically. Essentially, the second matrix forms a vector space with eigenvectors as its faces vectors. Both of these matrices are n by n matrices. The resulting matrix consists of n eigenvectors scaled by their corresponding eigenvalues. We can also express this matrix as the product of a matrix of eigenvectors and a diagonal matrix, where the diagonal elements are the eigenvalues. Let's denote the second matrix as D and the first matrix as P. Then, the matrix above here is also P. We can now simplify the equation with symbols as AP equals PD. By multiplying the inverse matrix of P on both sides of the equation, we get A equals PDP inversed. Remember, if you multiply a matrix by its inverse, you get an identity matrix as a product. Let's explore the meaning of matrix diagonalization. Matrix D in the equation only holds information of eigenvalues. Matrix A can be represented as a product of three matrices. The first matrix is composed of eigenvectors of the matrix. The second matrix holds the eigenvalues as its diagonal entries. And lastly, the third matrix is the inverse of a matrix composed of eigenvectors. We can decompose matrix A into the three parts. Earlier, we labeled each matrix as P, D, and the inverse of P. Matrix diagonalization is the process of decomposition of a matrix. Let's explore how linear algebra can be applied to principal components analysis. PCA is frequently used in data analysis and artificial intelligence, and it's one of the methods of dimension reduction. First of all, let me explain why we need dimension reduction in artificial intelligence. First, we compress high-dimensional data to lower dimensions. Additionally, by reducing the dimensionality of the data, we eliminate noise within it. In a sense, we reduce the data dimensions from n to m, where m is less than n, through dimension reduction. However, we cannot randomly eliminate any dimension in the data. Instead, we retain m meaningful data while discarding n-m meaningless dimensions. For example, if the data is three-dimensional, we keep two meaningful dimensions and eliminate one unnecessary dimension. However, when eliminating unnecessary dimensions, instead of simply discarding them, we transform the coordinate space before elimination. PCA is a method of dimension reduction that eliminates unnecessary dimensions within the transformed coordinate space. So, how do we determine which dimension is meaningful and which is not? First, we start by normalization. Suppose we have data x. To normalize the data, we subtract the mean of the data first, and then divide by the standard deviation of x. Why do we need to normalize data? If we examine the dimensions of the data, we may find that some dimensions have a range between 0 and 100, while others might range between 0 and 1, or negative 100 to 100. However, some dimensions with a range between 0 and 1 might be more important than those with a wider range. Thus, by normalizing the data, we can standardize each dimension to have a range consistent with the standard normal distribution. Step 2 involves calculating the covariance matrix. We utilize the formula displayed on the screen to derive this matrix. From step 1, we have normalized data. When we examine the normalized data more closely, we find that some data fluctuates with short cycles, while others change slowly with longer periods. Some data may even fluctuate more rapidly with shorter cycles than this. We regard rapidly fluctuating data as meaningful, while data with slower fluctuations are deemed unnecessary, as they convey less information. The covariance matrix not only contains information about its own variance, but also the relationships with other n-1 data. For instance, consider data number 1 and data number 2. Let's visualize the variances of these datasets. Given that both datasets fluctuate with the same cycle, we might question the necessity of retaining both datasets rather than utilizing just one of them. Suppose we have a covariance matrix V. After we find the eigenvalues and eigenvectors of this matrix, we can decompose it using matrix diagonalization. In the matrices P and D, which contain the eigenvectors and eigenvalues respectively, we can find information about the variances of the data, since the covariance matrix shows how data relate to each other. As mentioned earlier, we can identify pairs of data that exhibit similar patterns using the covariance matrix. Using the eigenvalues from matrix D, we can determine which data is important and which is not. A high eigenvalue signifies important data, while a low eigenvalue suggests less significance, indicating that we might consider dropping the corresponding data. In the matrix D obtained through matrix diagonalization, we have n eigenvalues from lambda 1 to lambda n. When arranging the eigenvalues in matrix D, we order them by their magnitude. Within matrix D, we retain the top m eigenvalues while discarding the rest, as higher eigenvalues indicate greater significance. We also have matrices P and P inverse surrounding matrix D. Similarly, we preserve only the first m eigenvectors with highest eigenvalues from these matrices while discarding the rest. This process reduces the data's dimensionality by retaining only the most important components. Now let's see how the dimensionality of data can be reduced. The dimension of the reduced matrix P inverse is m by n, while the dimension of our original data matrix A is n by n. By multiplying matrix A by matrix P inverse, we obtain a new matrix A with reduced dimension. To summarize, PCA is one of the important examples of applications of eigenvalues and eigenvectors, and it's frequently used in data processing. So remember how eigenvectors and eigenvalues are applied to other fields outside of linear algebra. Now, we're going to explore matrix exponentials. Although matrix exponentials don't appear frequently in image processing or natural language processing, they are significant in understanding a random walk or Markov decision process, which are decision-making processes. So it would be beneficial to learn about matrix exponentials. Suppose we have a matrix with entries 1, 2, 3, and 4. The exponential of the matrix is not a matrix with values E1, E2, E3, and E4. The definition of exponential of matrix A resembles Taylor's theorem. The mathematical definition of a matrix exponential is written on the board. Its mathematical definition is entirely different from exponentiating each individual entry. Matrix exponentials have the following properties. Let's explore each property in detail. The first two properties are similar to the properties of scalar exponentials. However, the third property is especially important. Suppose the function f of x is e to the x. Then the derivative of f of x is also e to the x. This property holds for matrices as well. When A is a matrix, the derivative of e to the at is just a times e to the at. Because of this simple property, we use matrix exponentials often in AI paper. Our last property is also very important. When we decompose an exponential of a matrix with matrix diagonalization, every matrix stays the same except for the central matrix, meaning that eigenvectors don't change. We often use matrix exponentials when we want to find the solution to linear systems. Suppose the values of x of t vary with time, and they are also influenced by the velocity. We define x of t as a naught times the exponential of at plus b. Then the derivative of x of t is a naught times a times the exponential of at. If we substitute a naught times exponential of at plus b into x of t in the formula above, we get a naught times a times exponential of at plus ba. Thus, ba equals 0, and we can drop b in x of t. Therefore, x of t equals a naught times exponential of at. To summarize, when we want to observe changes in values over time, the solution of the linear system often involves a matrix exponential. The last topic we'll cover today is the pseudo-inverse matrix. Let's consider a matrix A and a vector B, where their relationship is represented by a matrix vector multiplication. If we multiply both sides of the equation by the inverse of matrix A, we get x equals A inverse times B. However, if A is not a square matrix, meaning it's a rectangular matrix, then the rank of A is less than n. Consequently, the matrix doesn't have an inverse. For instance, if vector x is in Rn and vector b is in Rm, matrix A is an m by m matrix, and it doesn't have an inverse. However, even though the rectangular matrix A doesn't have an inverse, we can determine its pseudo-inverse matrix. Instead of multiplying the inverse of A on both sides, we multiply the transpose of matrix A. Initially, A is an m by n matrix, x is a vector in Rn, and b is a vector in Rm. The dimension of the transpose of matrix A is n by m. Thus, we can write n by m times m by n times n by 1 equals n by m times m by 1. The dimension of the product of these two matrices is n by n. so we can determine an inverse of the product. This time, we'll multiply the inverse of A transpose times A on both sides of the equation. The dimension of the inverse of the product is n by n, and the dimension of A transpose is n by m, and the dimension of B is m by 1. Thus, the dimension of the final product is n by 1. Does this final product provide a complete explanation of vector x? It depends on the sizes of m and n. Suppose m equals 3 and n equals 100. Through the matrix vector multiplication, the dimension of x has been decreased from 100 to 3, which means the information contained in x has been compressed to a lower dimension. And during the process, some information can be lost. Thus, complete recovery of information would be impossible. X will partially recover its information as much as B can explain. However, when m is much larger than n, B contains much more information than x, meaning that x can completely recover its information. Pseudo-inverse matrices are commonly used in AI research papers, so it's worth noting the concept of the information recovery process with pseudo-inverse matrices. So far, we have covered various topics in linear algebra, but there's one very important key point you must remember: the geometric meanings of the concepts. Throughout the lecture, we explore the geometric interpretations of matrices, inverse matrices, rank, determinants, matrix vector multiplication, and so on. We also learned about their applications in neural networks and the attention mechanism. A significant part of linear algebra revolves around matrix multiplication, or multiplication between matrices and vectors, which are commonly used when building AI models. We also learned about transformation of space through matrix multiplication. With matrix multiplication, we can not only rotate or tilt space, but also increase or decrease dimensions. Moreover, if the inverse of a matrix does not exist, information can be lost during the transformation process. Understanding these geometric interpretations of concepts is crucial when developing your own AI models or reading AI research papers. While you can review linear algebra by solving problems in textbooks, I highly recommend picking an AI research paper and trying to understand how the geometric meanings of the concept we've learned in the lecture are applied. That's it for today's lecture, and thank you so much for listening. See you at the next lecture.